Okay everyone, so this lesson is going to be talking about the forces of flight, so the actual physical forces that act upon an aircraft while it is in the air. So make sure you have your engineering notebooks ready and let's get started.
This lesson is on 1.2.5 Aerodynamic Forces. The big concept of this lesson is that you will learn how aircraft take flight through their ability to generate lift. As fluid flows over an airfoil, lift and drag are generated, which can be calculated using the lift equation. You will learn how to apply this equation. So let's take a look at the lift equation. Now this equation can be really intimidating to start off with, but when you break it into smaller pieces, it's actually not so bad. So first of all, lift is determined experimentally and combines several factors, which include the shape and angle of attack. And when we refer to shape, we're talking about the shape of the airfoil. Now the original formula is the coefficient of lift is equal to 2L, okay, which L is for lift, over A, which is for the wing area, P, which is for density, which is in kilograms over meters cubed, and V squared, which is our velocity in meters over second squared. The alternate format of this is the coefficient of lift is equal to lift over dynamic pressure, PA, which we get from just regular generic weather-based sources, and A, which is our wing area in meters squared. So let's take a look at applying the lift equation. Let's say a Cessna 172 from activity 122, step number 2, takes off successfully from Denver, Colorado during an average day in May. So 22 OC with a standard pressure of 101.3 kilopounds, and assume that the takeoff speed is 55 knots or 102 kilometers per hour. What is the minimum coefficient of lift needed at the point where the aircraft just lifts off the ground? The Cessna wing area is 18.2 meters squared, and the weight is 2,328 pounds. I'm going to pause this here and give you some time to look at this equation. If you need to see the lift formula again because you didn't copy it into your notes, the slides are linked in our weekly agenda. Okay, so let's take a look at this answer. The first thing we have to do is we have to convert mass into weight. So weight equals mass times gravity. So therefore we take 1,056 kilograms and multiply it by 9.81. Then we have 10,359. Then we have to convert our velocity. That gives us 28.3 meters per second. Then we have to take a look at calculating our air density. So using the information from the problem, we're going to plug in the different components that we need in order to solve for air density, giving us 1.196 kilograms per meters cubed. We can then calculate the coefficient of lift, assuming that lift equals weight. So with the assumption that lift is equal to weight, we can then take 10,359 newtons, multiplied by 2, 18.2 meters squared, because that's the area of the wing, our density that we calculated, which is 1.196, and then our velocity at 28.3. This is going to give us a coefficient of lift that is equal to 1.19. This means that at the point that the lift that we have just enough lift to get the wheels of the Cessna off the ground is 1.19. So now that we've talked about calculating lift, let's take a look at the actual airfoil. And specifically, the boundary layer. So fluid molecules stick to an object's surface, and that creates a boundary layer of slower moving fluid. And the boundary layer is crucial to wing performance. If you look at the diagram here, you will see that we have a specific area that is our boundary layer. That's the layer that is closest to the airfoil. That's where our slower moving fluid occurs, and this is crucial in order for us to create lift on any aircraft. So airflow over an object is slower the closer it is to the object's surface. The airflow remains smooth until critical airflow velocity. The airflow close to the object becomes turbulent at that point. You can see that down here in the diagrams. So here we have our laminar flow, So across our boundary layer, it's smooth. Once we get to a specific velocity, we then begin to get turbulent air at the boundary layer. So now let's take a look at the Reynolds number, or RE. The Reynolds number is a representative value to compare different fluid flow systems. An object moving through a fluid disturbs molecules, and that motion generates aerodynamic forces. So let's talk about how an angle of attack affects lift. Well, lift increases with the AOA up to the stall angle. So, the more we increase the angle of attack of an airfoil, the more lift we're going to create, up to a certain point. If you look in this graph, the more the angle of attack increases, the more lift we generate, up to this point where we stall out. That means that lift is no longer occurring, and we actually see a decrease in lift begin to start. Now let's bounce back to that Reynolds number. The Reynolds number is the ratio of inertial, or resistant to change forces, to the viscous, or sticky forces. And the Reynolds number is a dimensionless number. To calculate the Reynolds number, we have a couple of different formula setups. First of all, we have the Reynolds number being equal to fluid density and velocity and the length of fluid travel, or we have the Reynolds number equal to velocity and the fluid velocity and the length of fluid travel over kinematic viscosity. Now you'll notice there's a slight difference in these two V's. This V is a completely vertical V, which is velocity. This is a slightly curved V. That is the Greek letter V. Not exactly remembering what that letter is, but that stands for kinematic viscosity. So let's take a turn at applying the Reynolds number. So let's say a P3 Orion is cruising at 820 kilometers per hour, 509 miles per hour, at an altitude of 4,023 meters, or 13,198 feet. Assume a fluid viscosity coefficient of 1.65 times 10 to the negative fifth. What is the average Reynolds number along a wing cross-section measuring 1.1 meters, 3.6 feet, from leading edge to the trailing edge? So the following components that you'll need to calculate the Reynolds number are below. Take a moment to try and solve this problem. So let's take a look at the answer. First, we have to calculate our air temperature. So by calculating the air temperature, we know that we have negative 11.1 degrees centigrade. And then we have to calculate our air pressure, which then gets us to 61.5. We can convert our velocity to give us 227.8. And then we can count our Reynolds number. So by plugging in all the variables we have just solved for, our Reynolds number equals 12,408,000. So now let's take a look at the coefficient of drag. The coefficient of drag, just like the coefficient of lift, is determined experimentally and combines several factors, including shape and angle of attack. The formula for coefficient of drag can be set up in two ways. First, we have the coefficient of drag is equal to 2 times drag over the area of the wing multiplied by the density multiplied by the velocity squared. We can also set up the coefficient of drag as drag over dynamic pressure multiplied by the wing area. So let's take a look at how object shapes affect the coefficient of drag. The shape of an object has a very great effect on the amount of drag. If we have a flow moving in this direction, a flat plate is going to have significantly more drag than an airfoil. So let's take a look at applying the drag equation. Let's say that the same Cessna 172 from activity 122 step number 2 takes off under the same conditions as described earlier in this presentation. How much drag is produced when the wing is configured such that the coefficient of drag is 0.05? You should be able to look at the math that you did for the sample problem earlier to be able to plug in the same variables to be able to complete this problem. Take a moment to do so. So to calculate the drag, we plug in the variables from the first problem, and we end up with a coefficient of drag that is equal to 436 newtons.
Okay, so that wraps up forces of flight. We have learned how we have a balancing act of forces on an aircraft while it's in the air, and we have learned how we have to manipulate that balancing act to control an aircraft. So let's take a closer look at this in class, and I will see you soon. Bye!